Hello there, everyone. Picture this. You're standing on the frozen surface of Europa, Jupiter's ice-covered moon, staring out at a landscape that looks like the end of the world. The temperature hovers around -200 degrees Fahrenheit. Radiation from Jupiter bombards everything in sight with enough energy to sterilize a human in minutes. The atmosphere is thinner than a whisper, and the nearest star that could provide warmth is over 400 million miles away. By every measure we use to define a habitable world, this place is absolutely, completely, utterly dead. And yet, beneath your feet, locked under miles of solid ice, there might be more life than exists in all of Earth's oceans combined. Welcome to the revolutionary shift happening in astrobiology right now. For decades, scientists searched for alien life by looking up at the stars, focusing on planets in the so-called Goldilocks zone, that perfect distance from a star where water stays liquid on the surface. But we've been looking in the wrong place entirely. The real action isn't happening on planetary surfaces exposed to the cosmos. It's happening underground, in hidden oceans, buried ecosystems, and subterranean worlds that exist completely independent of starlight. This isn't just some wild theory cooked up by science fiction writers. This is hard science backed by discoveries that are rewriting everything we thought we knew about where life can exist. And the implications are staggering. If most alien life exists underground or under ice, then the universe might be absolutely teeming with living organisms in places we never thought to look. But here's the thing that will blow your mind. We don't need to travel to distant star systems to prove this concept. The evidence is right here in our own solar system, hiding beneath the surfaces of worlds we've dismissed as dead for generations. Mars, Europa, Enceladus, and even our own Earth are teaching us that the subsurface might be the most common habitat for life in the universe. So forget everything you think you know about alien worlds. Forget the Hollywood images of green planets with breathable atmospheres and pleasant temperatures. The real alien biosphere is dark, cold, and buried so deep that sunlight has never touched it. And by the time we're done exploring this topic, you'll understand why the search for extraterrestrial life has fundamentally shifted from looking at planetary surfaces to drilling beneath them. Let's start with the obvious question. Why would life choose to hide underground when the surface seems so much more appealing? The answer lies in understanding just how brutal and unforgiving most planetary surfaces really are. Take Mars, our closest planetary neighbor and humanity's favorite target for finding alien life. On the surface, Mars looks almost inviting in photographs. Rolling red hills, dramatic canyons, and polar ice caps that remind us of Earth's winter landscapes. But those images are deceiving in the most dangerous way possible. The reality of Mars' surface is a combination of lethal factors that would destroy any known form of life within minutes. The atmosphere on Mars is less than 1% as thick as Earth's, which means it provides virtually no protection from cosmic radiation. Every day, high-energy particles from deep space slam into the Martian surface with enough force to shred DNA and destroy organic molecules. The temperature swings are equally devastating, ranging from a relatively balmy 70 degrees Fahrenheit at the equator during summer to -200 degrees during polar winter. But temperature and radiation are just the beginning of the problem. The soil itself is toxic. Martian regolith contains chemicals called perchlorates, which are so reactive and poisonous that they can kill most Earth organisms on contact. When these perchlorates are exposed to the UV radiation constantly bathing Mars's surface, they become even more lethal, creating a sterilizing cocktail that would eliminate any biological material within hours. Scientists have tested this combination of factors in laboratory conditions, and the results are sobering. While some Earth organisms can survive cold temperatures and others can handle radiation, and still others can tolerate toxic chemistry, Almost nothing can survive when all these lethal factors are combined simultaneously. The surface of Mars isn't just hostile to life, it's actively genocidal. But here's where it gets interesting. Just a few feet beneath that deadly surface, conditions change dramatically. The soil provides protection from radiation, the temperature stabilizes, the chemical environment becomes more neutral, and most importantly, there might be liquid water. Recent research has revealed that the Martian subsurface could be riddled with networks of liquid brine, salty water that stays liquid even at temperatures well below the freezing point of pure water. These underground water systems could extend for miles beneath the surface, creating a hidden hydrosphere that dwarfs anything visible on Mars today. And here's the kicker. If there's groundwater on Mars, there's almost certainly enough chemical energy to support microbial life. The same research that identified these subsurface water systems also calculated the energy available from water-rock interactions, radioactive decay, and chemical gradients. The numbers are stunning. The energy density in Mars' subsurface could be comparable to the deep underground environments on Earth where thriving microbial communities have been discovered. This isn't speculation anymore. We have direct evidence from Earth that life can flourish in exactly these kinds of subsurface conditions. In places like the Kidd Creek Mine in Canada, scientists have found complex ecosystems living more than 2 miles underground in water that hasn't seen sunlight for over 1 billion years. These deep Earth communities survive by metabolizing sulfates and other minerals dissolved in ancient groundwater. They create their own food through chemical processes that have nothing to do with photosynthesis or surface-derived nutrients. They've been living in complete isolation from the surface world for longer than complex life has existed on Earth's surface. And they're not just surviving, they're thriving. The microbes in Kidd Creek live in water that's extremely salty, incredibly hot, and filled with dissolved gases, including hydrogen, which serves as their primary energy source. The ecosystem operates like a biological machine that runs on chemistry instead of sunlight. And if this kind of life can exist 2 miles beneath Canada, there's no reason it couldn't exist 2 miles beneath the surface of Mars. But Mars is just the beginning. The real game changers are the ice-covered moons of the outer solar system. Worlds that harbour subsurface oceans containing more water than all of Earth's seas combined. Europa, Jupiter's 4th largest moon, is perhaps the most promising target for finding alien life in our solar system. From the surface, Europa looks like a giant cue ball, covered in a smooth shell of water ice that reflects sunlight like a cosmic mirror. But that ice isn't solid all the way through. Beneath a crust that's probably 15 to 20 miles thick lies an ocean that could be 60 to 100 miles deep. Think about that for a moment. Europa's hidden ocean contains roughly twice as much water as all of Earth's oceans combined. It's been liquid for billions of years, heated by tidal forces from Jupiter's immense gravity. And it's completely protected from the radiation environment that would sterilize the surface. But Europa's ocean isn't just a big tank of sterile water. Recent evidence suggests it's chemically active and energy-rich. Radiation from Jupiter constantly bombards Europa's ice shell, breaking apart water molecules and creating hydrogen, oxygen, and other reactive compounds. Over geological time, these chemical products migrate through the ice and into the subsurface ocean, creating a continuous supply of chemical energy that could power biological processes. Even more exciting, some scientists believe Europa's ocean floor might be dotted with hydrothermal vents, underwater hot springs, where superheated water, rich in minerals, erupts from the seafloor. On Earth, these hydrothermal vents support some of the most diverse and productive ecosystems on the planet, home to giant tube worms, specialized bacteria, and creatures that exist nowhere else. If Europa has similar hydrothermal systems, its subsurface ocean could be absolutely teeming with life. We're talking about ecosystems that could rival the biodiversity of Earth's rainforests, hidden beneath miles of ice on a moon orbiting Jupiter. And Europa isn't alone. Enceladus, one of Saturn's moons, offers an even more direct window into subsurface ocean chemistry. Enceladus regularly erupts geysers of water vapor and ice particles from cracks near its south pole, essentially giving us free samples of its subsurface ocean. When the Cassini spacecraft flew through these plumes, it detected a chemical treasure trove, molecular hydrogen, which could serve as an energy source for life. Complex organic molecules, including amino acids, the building blocks of proteins. Rocky silica particles that suggested hydrothermal activity on the ocean floor. Everything necessary for life as we know it. But here's what makes Enceladus truly special. Those complex organic molecules aren't just breakdown products from space weathering. They're fresh, complex compounds that indicate active chemistry happening right now in the subsurface ocean. Enceladus isn't just a dead world with some interesting chemistry. It's potentially a living world with an active biosphere hidden beneath its icy shell. The implications of this research go far beyond our solar system. If life prefers subsurface environments even in our own cosmic neighborhood, then the number of potentially habitable worlds in the universe increases by orders of magnitude. Traditional astrobiology focused on planets in the habitable zone around stars, that narrow band where surface temperatures allow liquid water. But subsurface oceans don't depend on starlight for warmth. They can be heated by radioactive decay, tidal forces, chemical reactions, or even the energy from cosmic radiation itself. This means that moons around gas giant planets, rogue planets drifting between the stars, and worlds in the outer reaches of solar systems could all potentially harbor subsurface biospheres. The universe might be filled with living worlds that look completely dead from the outside. We're not just talking about simple microbial life either. Earth's subsurface biosphere contains as much biomass as the entire surface biosphere, with potentially even greater genetic diversity. If the same scaling applies to other worlds, then the subsurface could represent the dominant form of life in the universe. Form of life in the universe. This radical shift in thinking has led scientists to develop an entirely new framework for understanding habitability called the radiolytic habitable zone. Unlike the traditional Goldilocks zone that depends on perfect distance from a star, the radiolytic habitable zone looks at places where cosmic radiation interacts with water ice to create energy-rich environments. Here's how it works, and it's absolutely mind-bending. High-energy cosmic rays, the same radiation that we've always considered deadly to life, strike ice or rock and break apart water molecules. This process, called radiolysis, creates hydrogen gas, oxygen, and other reactive compounds that can serve as food for microbial life. Instead of needing warmth from a nearby sun or heat from a planet's core, organisms can literally feed off the energy from cosmic radiation. This completely flips our understanding of what makes a world habitable. Radiation isn't just a destroyer of life anymore. Under the right conditions, it becomes a sustainer of life. And those right conditions exist throughout the universe in subsurface environments where water ice meets cosmic rays. The energy calculations are staggering. Scientists have determined that radiolytic processes could provide enough chemical energy to support microbial ecosystems for billions of years. We're not talking about barely surviving organisms clinging to existence. We're talking about potentially thriving communities with energy budgets comparable to some of Earth's most productive deep-sea environments. But the real breakthrough came when researchers started looking at Earth's own subsurface biosphere with fresh eyes. What they discovered changed everything we thought we knew about the limits of life on our own planet. Deep beneath the continents, in groundwater systems that extend miles below the surface, scientists have found one of the most extensive ecosystems on Earth. This isn't just a thin film of microbes scratching out a living in harsh conditions. It's a massive, three-dimensional biosphere that rivals the productivity of surface ecosystems. The numbers are almost incomprehensible. Earth's continental subsurface contains billions of tons of living biomass, representing a significant fraction of all life on the planet. These organisms live in environments that would be considered impossible by surface standards. Temperatures that exceed the boiling point of water, pressures that would crush surface organisms instantly, chemical conditions so extreme they would dissolve most biological materials. And yet, life has not just adapted to these conditions, it has flourished. The genetic diversity in subsurface environments may actually exceed that of surface ecosystems. Scientists have discovered entirely new branches of the tree of life living in deep groundwater, organisms so different from surface life that they represent fundamentally new ways of being alive. These deep subsurface organisms have evolved metabolic strategies that seem almost magical. Some derive energy from radioactive decay, literally feeding off the breakdown of uranium and other radioactive elements in rock. Others metabolize hydrogen gas produced by water reacting with iron minerals. Still others consume organic compounds that have been buried for millions of years, breaking down ancient biological materials that predate complex life on Earth's surface. The timescales involved are equally mind-boggling. Some of these subsurface ecosystems have been isolated from the surface for hundreds of millions of years. They represent evolutionary experiments that have been running independently since before dinosaurs walked the Earth. And they're not evolutionary dead ends. They're actively evolving, adapting, and diversifying in their underground kingdoms. This discovery has revolutionized our understanding of life's limits and possibilities. If Earth's subsurface can support such extensive and diverse ecosystems, then the subsurface environments of other worlds become incredibly promising targets for finding alien life. But we don't have to limit ourselves to speculation. The technology for exploring subsurface environments on other worlds is advancing rapidly, and some of the most ambitious missions in space exploration history are being designed to drill into alien underground worlds. Mars represents the most immediate target for subsurface exploration. The European Space Agency's ExoMars mission includes a rover specifically designed to drill up to 6 feet beneath the Martian surface, deep enough to reach regions where organic molecules could survive the harsh surface conditions. This isn't just a fishing expedition. It's a targeted search based on solid scientific evidence that Mars' subsurface could harbor active microbial communities. The drilling technology being developed for Mars exploration is remarkably sophisticated. Engineers have designed compact drilling systems that can operate in the extreme cold and low atmospheric pressure of Mars, while maintaining sterile conditions to avoid contaminating potential alien ecosystems. These systems can extract pristine samples from multiple depths and analyze them with instruments sensitive enough to detect individual organic molecules. But Mars drilling missions are just the beginning. The real prizes are the subsurface oceans of the outer solar system, and scientists are developing increasingly ambitious plans to reach them. The proposed Tigra mission to Enceladus represents the next generation of subsurface exploration. This mission would combine an orbiter, lander, and drilling system specifically designed to penetrate Enceladus's ice shell and directly sample the subsurface ocean. The technical challenges are immense, but the potential payoff is even greater. Imagine a robotic probe melting through 20 miles of ice, descending through an alien ocean that has never been touched by sunlight, and discovering ecosystems that have been evolving independently for billions of years. The biological discoveries could be more significant than anything in the history of science. And the timeline for these missions is shorter than you might think. Within the next 2 decades, we could have definitive answers about whether life exists in the subsurface oceans of Europa, Enceladus, and other ice-covered worlds. We could be on the verge of discovering that the universe is absolutely teeming with life, most of it hidden beneath the surfaces of worlds we previously dismissed as dead. The search strategies being developed are incredibly sophisticated. Rather than randomly drilling into ice, scientists are using thermal imaging and gravitational measurements to identify the most promising locations. They're looking for areas where the ice is thinnest, where thermal activity suggests active ocean circulation, and where chemical signatures indicate the presence of organic compounds. These aren't just exploratory missions. They're designed to answer fundamental questions about the nature of life itself. Do alien organisms use the same biochemistry as Earth life? Or have they evolved entirely different solutions to the challenges of survival? How complex can life become in the absence of sunlight? Are there entire ecosystems of multicellular organisms living in alien oceans? The metabolic possibilities in these environments are fascinating. On Earth, deep-sea hydrothermal vents support ecosystems based on chemosynthesis rather than photosynthesis. Bacteria convert chemical energy from hydrogen sulfide and other compounds into biological energy, forming the base of food chains that include some of the most unusual organisms on our planet. In Europa's ocean, similar processes could support ecosystems based on the chemical energy produced by radiation interacting with the ice shell. Sulfate-reducing bacteria could thrive in the salty depths, creating the foundation for more complex communities. Methanogenic organisms could produce methane as a waste product, creating chemical signatures that future missions could detect. The temperature challenges in these alien oceans are significant, but not insurmountable. While Europa's ocean probably hovers near the freezing point of saltwater, Earth organisms called psychrophiles have proven that life can remain active at temperatures well below zero. Some of these cold-loving microbes can continue metabolizing and reproducing at temperatures that would freeze most organisms solid. Even more intriguingly, the combination of salt tolerance and cold adaptation could allow organisms to thrive in conditions that seem impossible. Halophilic bacteria that love salt and psychrophilic bacteria that love cold could represent the perfect combination for surviving in alien subsurface oceans. The energy sources available in these environments are more diverse than most people realize. Beyond the chemical energy from radiolysis and hydrothermal activity, there are osmotic gradients between different water masses, kinetic energy from tidal currents, and even energy from the magnetic fields generated by conducting saltwater moving through the magnetic fields of gas giant planets. This abundance of energy sources means that subsurface oceans could support not just simple microbial life, but potentially complex ecosystems with multiple trophic levels. We could be looking at alien food chains that rival the complexity of Earth's deep-sea communities. The preservation potential in these environments is another crucial factor. Unlike planetary surfaces where organic molecules are quickly destroyed by radiation and chemical weathering, subsurface environments can preserve biological signatures for millions or even billions of years. This means that even if life in these environments is currently dormant or extinct, we might still be able to find evidence of past biological activity. Recent laboratory experiments have shown that amino acids, the building blocks of proteins, can survive in ice for extended periods even when exposed to radiation. On Europa, amino acids could remain detectable at depths of just 8 inches in some regions. On Enceladus, they could survive at the very surface in areas where fresh ice has recently been deposited by geyser activity. These findings provide specific guidance for future missions, indicating exactly where to look and how deep to drill to find the best preserved biosignatures. The search for alien life is becoming increasingly focused and strategic, guided by hard data rather than wishful thinking. the implications extend far beyond our solar system. If subsurface life is common in our cosmic neighborhood, then it's probably common throughout the universe. Every star system with gas giant planets could harbor multiple worlds with subsurface biospheres. Rogue planets drifting between the stars could maintain active ecosystems heated by radioactive decay and insulated by thick ice shells. We might be living in a universe where surface life like Earth's is actually the exception, and subsurface life is the rule. The galaxy could be filled with hidden biospheres, invisible to our telescopes, but teeming with organisms that have never seen starlight. This possibility is reshaping the entire field of astrobiology and influencing how we design future space missions. Instead of focusing solely on potentially habitable planets around other stars, scientists are increasingly interested in the moons of gas giant planets and the subsurface environments of worlds throughout our own solar system. The next chapter in the search for alien life won't be written by looking up at the stars. It will be written by drilling down into alien worlds, melting through ice shells, and exploring the hidden oceans that may represent the most common habitat for life in the universe. The timeline for these revolutionary discoveries is accelerating faster than anyone expected. Right now, as you're watching this video, robotic missions are already collecting data that could rewrite our understanding of life in the universe. The Perseverance rover on Mars is analyzing subsurface samples with instruments sensitive enough to detect organic molecules that have been preserved in Martian rock for billions of years. The James Webb Space Telescope is studying the atmospheric compositions of distant worlds, looking for chemical signatures that could indicate subsurface biological activity. But perhaps the most exciting developments are happening in laboratories right here on Earth, where scientists are recreating the conditions found in alien subsurface environments and discovering that life is far more adaptable than we ever imagined. In research facilities across the globe, astrobiologists are subjecting Earth organisms to the extreme conditions found beneath the surfaces of other worlds. They're freezing microbes in saltwater brines that mimic Europa's ocean chemistry. They're exposing bacteria to the radiation levels found near Jupiter. They're testing whether organisms can survive in the low temperature, high pressure conditions that exist miles beneath planetary surfaces. The results are consistently surprising. Life keeps finding ways to survive in conditions that should be absolutely lethal. Scientists have discovered bacteria that can remain viable after being frozen in ice for hundreds of thousands of years. They've found microorganisms that actually thrive in high radiation environments, using the energy from radioactive decay to power their metabolism. They've identified organisms that can survive in water so salty it would instantly dehydrate most living things. These experiments aren't just academic exercises. They're providing a roadmap for what kinds of life we might find in alien subsurface environments and how to detect it when we get there. The detection methods being developed are becoming increasingly sophisticated. Instead of just looking for obvious signs of life like cells or DNA, scientists are learning to recognize the subtle chemical fingerprints that biological processes leave behind. They're studying isotope ratios that could indicate metabolic activity. They're analyzing mineral formations that might preserve evidence of ancient microbial communities. They're developing instruments that can detect individual amino acids preserved in ice samples. These biosignature detection techniques are being tested in Earth's most extreme environments, places that serve as natural laboratories for understanding alien life. In Antarctica's dry valleys, where conditions closely resemble those on Mars, researchers are learning how to distinguish between biological and non-biological chemical processes. In deep ocean environments that never see sunlight, they're studying how subsurface ecosystems might function on other worlds. The Antarctic research is particularly relevant because the continent's subsurface environment shares many characteristics with what we expect to find on Mars and the icy moons of the outer solar system. Beneath Antarctica's ice sheets, scientists have discovered extensive networks of liquid water, including subglacial lakes that have been isolated from the surface for millions of years. Lake Vostok, buried beneath 2 miles of Antarctic ice, represents one of the most Mars-like environments on Earth. This massive freshwater lake has remained liquid for at least 15 million years, completely cut off from sunlight and surface nutrients. When Russian scientists finally managed to drill through the ice and sample the lake water, they found it wasn't sterile. Despite the extreme isolation and harsh conditions, Lake Vostok contains active microbial communities. These Antarctic discoveries provide direct evidence that large bodies of liquid water can remain biologically active even when completely isolated beneath thick ice sheets. If life can persist in Lake Vostok for 15 million years, there's no reason it couldn't persist in Europa's ocean for billions of years. The energy calculations for these isolated ecosystems are particularly intriguing. In environments like Lake Vostok, organisms derive energy from chemical processes that have nothing to do with surface photosynthesis. They metabolize dissolved minerals, consume organic compounds preserved in ancient ice, and even derive energy from the radioactive decay of elements in the surrounding rock. This chemical independence means that subsurface ecosystems can operate on completely different timescales than surface life. While surface ecosystems depend on the daily cycle of sunlight and the seasonal changes in solar energy, subsurface ecosystems can maintain steady-state conditions for geological periods. The stability of subsurface environments is actually one of their greatest advantages for supporting life. Surface conditions on most worlds are highly variable, with extreme temperature swings, radiation bombardment, and chemical weathering that constantly challenges living organisms. Subsurface environments, by contrast, maintain relatively constant conditions over millions or billions of years. This stability allows for long-term evolutionary processes that would be impossible on planetary surfaces. Subsurface organisms can evolve specialized adaptations to their specific chemical environments without having to deal with the constant environmental chaos that characterizes surface life. The genetic diversity studies coming out of Earth's subsurface research are absolutely staggering. Scientists have discovered that deep groundwater systems contain entirely new branches of the tree of life, organisms so genetically distinct from surface life that they represent fundamentally different approaches to being alive. Some of these deep subsurface organisms reproduce so slowly that their generation times are measured in centuries rather than hours or days. They've evolved metabolic strategies that allow them to survive on incredibly small amounts of energy, essentially living in slow motion compared to surface organisms. Yet despite their slow metabolism, these organisms maintain active genetic exchange and continue to evolve and adapt to their environments. The implications for alien life are profound. If Earth's subsurface can support such genetically diverse and evolutionarily active ecosystems, then alien subsurface environments could potentially harbor biological diversity that dwarfs anything we see on planetary surfaces. But the most revolutionary aspect of this research isn't just that subsurface life exists, it's that subsurface life might actually be more evolutionarily advanced than surface life in some respects. The extreme conditions in subsurface environments have driven the evolution of biochemical capabilities that don't exist in surface organisms. Deep subsurface bacteria have evolved enzymes that can function at temperatures and pressures that would destroy normal proteins. They've developed DNA repair mechanisms that can fix radiation damage more efficiently than anything found in surface organisms. They've created metabolic pathways that can extract energy from chemical sources that surface life can't even detect. These advanced biochemical capabilities suggest that if we do find alien life in subsurface environments, it might be far more sophisticated than we expect. Instead of finding simple microbes barely clinging to existence, we might discover organisms with biochemical abilities that exceed anything found on Earth's surface. The search strategies being developed for finding this alien subsurface life are becoming incredibly targeted and sophisticated. Rather than randomly sampling subsurface environments, scientists are developing comprehensive maps of where life is most likely to exist and how to detect it once we get there. For Mars, researchers have identified specific geological formations that would have provided the best conditions for subsurface life to develop and persist. These include areas where ancient hydrothermal systems would have created warm, chemically rich environments, regions where groundwater systems would have remained active for extended periods, and locations where radioactive elements in the rock would have provided continuous energy sources for biological processes. The drilling strategies for Mars missions are being designed to target these high-probability locations with surgical precision. Instead of drilling random holes and hoping to find something interesting, future Mars missions will use ground-penetrating radar, chemical analysis, and thermal imaging to identify the most promising subsurface targets before drilling begins. For the icy moons of the outer solar system, the search strategies are even more sophisticated. Scientists are using gravitational measurements to map the thickness of ice shells and identify areas where the subsurface ocean comes closest to the surface. They're analyzing the chemical composition of geyser plumes to determine which regions of the subsurface ocean are most chemically active. They're studying the magnetic field signatures that indicate where saltwater ocean currents are strongest. These detailed reconnaissance efforts are creating three-dimensional maps of alien subsurface environments that will guide future drilling and sampling missions. By the time we're ready to send probes to drill through Europa's ice shell, we'll know exactly where to drill and what we're likely to find when we get there. The technological challenges involved in these missions are immense, but they're not insurmountable. Engineers are developing drilling systems that can operate autonomously in the extreme conditions found on alien worlds. These systems need to be able to maintain sterile conditions to avoid contaminating alien ecosystems, operate in temperatures hundreds of degrees below zero, and communicate with Earth across distances of hundreds of millions of miles. The drilling technology being developed for Europa missions is particularly impressive. These systems will need to melt through 15 to 20 miles of solid ice while maintaining precise temperature and pressure control to avoid damaging any biological samples they encounter. They'll need to be able to analyze water samples in real time and transmit the results back to Earth before the samples freeze or degrade. But perhaps the most challenging aspect of these missions isn't technical, it's biological. If we do find alien life in subsurface environments, how will we know that it's actually alive and not just interesting chemistry? How will we distinguish between biological processes and non-biological processes that might produce similar chemical signatures? These questions are driving some of the most sophisticated research in astrobiology today. Scientists are developing increasingly sensitive methods for detecting the subtle differences between biological and non-biological chemistry. They're studying how biological processes create specific isotope ratios that can be distinguished from purely chemical processes. They're learning to recognize the complex organic molecules that can only be produced by living systems. The detection criteria being developed are incredibly rigorous. Finding a single organic molecule won't be enough to claim the discovery of alien life. Scientists will need to find multiple lines of evidence, including specific chemical signatures, isotope ratios, and molecular structures that can only be explained by biological processes. But when that evidence is found, and many scientists believe it will be found within the next 2 decades, it will represent the most significant discovery in human history. The confirmation that life exists in the subsurface environments of other worlds will prove that life is not unique to Earth and that the universe is filled with living systems we're only just beginning to understand. The philosophical implications are as profound as the scientific ones. If most life in the universe exists in subsurface environments, then our entire perspective on what it means to be alive will need to be reconsidered. We'll need to expand our definition of habitability beyond the narrow constraints of surface conditions and solar energy. We'll also need to reconsider our assumptions about intelligence and consciousness. If complex ecosystems can develop in subsurface environments, is it possible that intelligent life could evolve in these hidden biospheres? Could there be entire civilizations living beneath the surfaces of worlds that appear completely dead from the outside? These questions might seem like science fiction, but they're based on solid scientific evidence that subsurface environments can support complex, long-term biological processes. If Earth's subsurface can maintain active ecosystems for hundreds of millions of years, there's no fundamental reason why alien subsurface environments couldn't support even more complex biological phenomena. The search for subsurface life is also changing how we think about the future of human space exploration. If the most habitable environments in the solar system are located beneath planetary surfaces, then future human settlements might need to be built underground as well. Mars colonization plans are already incorporating this understanding. Instead of building surface habitats that would require massive amounts of shielding and life support systems, future Mars colonies might be located in natural underground spaces, like lava tubes or artificially excavated chambers, that provide natural protection from radiation and temperature extremes. The same principles apply to settlements on the moons of the outer solar system. Rather than trying to build habitats on the radiation-bombarded surface of Europa, future explorers might establish bases within the ice shell itself, taking advantage of the natural radiation shielding and the proximity to the energy-rich subsurface ocean. These underground human settlements would exist alongside whatever alien ecosystems we discover in subsurface environments. The challenge will be learning to coexist with alien life without disrupting the delicate chemical and biological balances that have been maintained for billions of years. The ethical considerations are complex and unprecedented. If we find thriving ecosystems in alien subsurface environments, do we have the right to establish human colonies in those same environments? How do we balance human exploration and settlement with the protection of alien biospheres that might represent billions of years of independent evolution? These questions don't have easy answers, but they're questions that humanity will need to confront within the next few decades as our exploration of subsurface environments advances from robotic reconnaissance to human settlement. The timeline for these developments is compressed in a way that would have seemed impossible just a generation ago. The combination of advancing drilling technology, increasingly sophisticated detection methods, and growing understanding of subsurface habitability means that we're approaching a moment when the discovery of alien life shifts from possibility to probability. Within the next decade, Mars drilling missions will be analyzing subsurface samples with unprecedented sensitivity. Within the next 2 decades, probes will be melting through the ice shells of Europa and Enceladus, directly sampling alien ocean water that has been isolated from the surface for billions of years. The biological discoveries from these missions could be more significant than anything in the history of science. We might find that alien life uses completely different biochemistry than Earth life, opening up entirely new possibilities for what it means to be alive. We might discover that complex ecosystems are common in subsurface environments throughout the solar system, suggesting that life is far more abundant in the universe than we ever imagined. Or we might find that subsurface life is so fundamentally different from surface life that it challenges our basic understanding of biology itself. The organisms living in alien underground oceans might have evolved solutions to the challenges of existence that are completely unknown on Earth. Whatever we find, it will represent a watershed moment in human understanding. The discovery of alien life, even microbial life, will prove that Earth is not unique, and that the processes that led to the emergence of life on our planet are operating throughout the universe. But the real revolution isn't just that we'll find alien life. It's that we'll find alien life in places we never thought to look, using energy sources we never considered, and surviving in conditions we thought were impossible. The universe is far stranger and more alive than we ever imagined, and most of that strangeness and life is hidden beneath the surfaces of worlds that look completely dead from the outside. The next chapter in the story of life in the universe won't be written on planetary surfaces under alien suns. It will be written in the dark, cold, hidden oceans and underground ecosystems that represent the true frontier of astrobiology. And we're closer to reading that next chapter than most people realize. The evidence keeps mounting from every corner of our solar system, and it's painting a picture that's both humbling and extraordinary. While we've been scanning distant star systems for radio signals and searching for planets with Earth-like atmospheres, the most compelling signs of alien life have been hiding right under our noses, literally beneath the surfaces of worlds we pass by every day. Consider the sheer scale of what we're dealing with. Earth's continental subsurface biosphere contains an estimated 15 to 23 billion tons of carbon in living organisms. That's hundreds of times more biomass than all humans combined, and it's living in conditions that would kill surface life instantly. These aren't just a few hardy microbes scratching out a miserable existence in the depths. We're talking about complex, interconnected ecosystems with their own food webs, predator-prey relationships, and evolutionary pressures. The metabolic diversity down there is staggering. Scientists have discovered organisms that eat sulfur, breathe iron, and derive energy from the radioactive decay of uranium. Some bacteria can survive being completely dried out for decades and then spring back to life when water returns. Others can repair radiation damage to their DNA faster than the radiation can cause it, essentially making them immortal in high radiation environments. But here's what really bends your mind. These subsurface organisms aren't evolutionary stragglers or primitive life forms that got left behind. Many of them represent the cutting edge of biological innovation. They've evolved biochemical machinery that operates more efficiently than anything found in surface life. Their enzymes work at temperatures that would melt normal proteins. Their cell membranes remain flexible at pressures that would crush surface organisms into paste. This isn't just academic curiosity. These discoveries are fundamentally changing how we approach the search for alien life, because they're showing us that biology is far more creative and adaptable than we ever imagined. If life on Earth can thrive in boiling acid, survive million-year droughts, and extract energy from radioactive rocks, then the range of environments where alien life could exist expands dramatically. The energy calculations alone are revolutionary. Traditional astrobiology focused on the habitable zone around stars because surface life depends on solar energy through photosynthesis. But subsurface life operates on completely different energy budgets. A single gram of uranium provides enough energy to support a microbial community for millions of years. Water flowing through fractured rock generates electrical currents that organisms can tap into directly. Even the slow decay of organic matter, buried millions of years ago, can sustain active ecosystems. These alternative energy sources are available throughout the universe. Every rocky planet contains radioactive elements. Every world with liquid water has chemical gradients that can be exploited for energy. Every icy moon experiences cosmic ray bombardment that creates reactive compounds. The universe is absolutely saturated with energy sources that subsurface life can utilize. And we're not just talking about energy for basic survival. Some subsurface environments on Earth are so energy-rich that they support organisms with generation times measured in hours rather than centuries. These aren't slow-motion ecosystems barely hanging on. They're dynamic, rapidly evolving biological communities that could potentially develop complexity rivaling surface ecosystems. The genetic studies coming out of deep subsurface research are rewriting textbooks. Scientists have discovered that many subsurface organisms exchange genetic material horizontally, sharing beneficial mutations across different species in real time. This creates evolutionary networks, where beneficial adaptations can spread through entire communities within generations rather than millennia. Some subsurface bacteria have genomes that are more complex than those of surface organisms, with sophisticated regulatory systems that allow them to switch between dozens of different metabolic strategies, depending on environmental conditions. They're like biological Swiss Army knives, equipped to handle whatever chemistry their environment throws at them. The implications for alien intelligence are mind-bending. If subsurface environments can support such genetic complexity and metabolic sophistication, could they potentially support nervous systems? Could there be alien organisms in subsurface oceans that have evolved information processing capabilities we haven't even imagined? This isn't wild speculation. Earth's subsurface organisms already demonstrate primitive forms of collective intelligence. Some bacterial communities coordinate their behavior across vast distances through chemical signaling networks. They can make group decisions about when to reproduce, when to go dormant, and how to respond to environmental changes. Scale that up to the massive subsurface oceans of Europa or Enceladus, add billions of years of evolution, and you start to see possibilities that challenge every assumption we've made about intelligence and consciousness. Could there be alien minds living in those hidden oceans, as different from human consciousness as we are from bacteria? The detection technologies being developed to answer these questions are becoming almost science fictional in their sophistication. Future Mars missions will carry instruments that can identify individual biological molecules in soil samples and determine whether they were produced by living organisms or chemical processes. These devices can distinguish between the hundreds of different isotope signatures that biological processes create, essentially reading the chemical fingerprints that life leaves behind. For the icy moons, scientists are developing even more ambitious detection strategies. The proposed Europa missions will carry hydrophones that can listen for sounds in the subsurface ocean, potentially detecting the acoustic signatures of biological activity. They'll use laser spectrometers to analyze the chemical composition of water samples in real time, identifying organic compounds that could only be produced by living systems. But perhaps the most revolutionary technology being developed is biological itself. Scientists are engineering extremophile bacteria that could serve as living sensors for alien life. These modified organisms would be designed to respond to specific biological signatures by changing color or producing detectable chemical signals. It's like creating biological Geiger counters that can sense life instead of radiation. The timeline for deploying these technologies is accelerating rapidly. NASA's Dragonfly mission to Titan, Saturn's largest moon, will land in the mid-2030s with instruments capable of detecting complex organic chemistry in Titan's subsurface. The mission will specifically target areas where liquid methane and water ice interact, creating conditions that could support exotic forms of life based on completely different chemistry than Earth organisms. Even more ambitious is the proposed Enceladus Life Finder mission, which would fly multiple times through Enceladus's geyser plumes, with instruments sensitive enough to detect individual cells if they exist in the subsurface ocean. The mission would essentially perform a biological census of an alien ocean without ever landing on the surface. These missions represent a fundamental shift in space exploration strategy. Instead of sending general-purpose scientific instruments and hoping to stumble across interesting discoveries, we're now designing highly targeted missions based on specific predictions about where alien life is most likely to exist and how to detect it. The statistical projections are staggering. Conservative estimates suggest that our solar system alone could contain a dozen or more worlds with active subsurface biospheres. Optimistic projections put that number closer to 50, including small moons, asteroids with liquid interiors, and regions of the outer planets where exotic chemistry could support life. Extrapolate those numbers across the galaxy, and you're looking at billions of worlds with subsurface ecosystems. The Milky Way could contain more living biomass in subsurface environments than exists on all planetary surfaces combined. We might be living in a galaxy where hidden life is the rule, and surface life like Earth's is a rare exception. The philosophical implications are staggering. If most life in the universe exists in subsurface environments, then our entire concept of what constitutes a living world needs to be reconsidered. A planet could appear completely dead from space while harboring more biological diversity than Earth beneath its surface. This realization is already changing how we interpret observations of distant planets. Atmospheric signatures that we once dismissed as purely geological might actually be evidence of subsurface biological activity. Chemical disequilibria in planetary atmospheres could indicate that deep biospheres are processing materials and releasing waste products into the air. The search for biosignatures is expanding beyond traditional markers like oxygen and methane to include more subtle indicators of subsurface life. Scientists are learning to recognize the complex chemical fingerprints that result from biological processes operating deep beneath planetary surfaces. Recent advances in quantum sensing technology are making it possible to detect these subtle biosignatures from orbit. Future space telescopes will be able to measure isotope ratios in planetary atmospheres with precision sufficient to identify biological processes occurring hundreds of kilometers beneath a planet's surface. But the real game changer will come when we start finding complex organic molecules in the subsurface samples returned by drilling missions. The discovery of amino acids, nucleic acids, or other biological macromolecules in Martian subsurface samples would provide definitive proof that life can emerge and persist in subsurface environments. Even more exciting would be the discovery of completely novel biochemistry in alien subsurface environments. Earth life is based on carbon chemistry and liquid water, but subsurface environments on other worlds might support forms of life based on silicon chemistry, liquid methane, or even more exotic possibilities. The energy density calculations for some of these exotic environments are remarkable. Titan's subsurface ocean contains dissolved ammonia that could serve as an antifreeze, allowing complex chemistry to occur at temperatures where water-based life would be impossible. The chemical gradients between Titan's methane-rich surface and water-rich interior could drive metabolic processes unlike anything found on Earth. Even more intriguing are the possibilities for life in the metallic hydrogen oceans that might exist deep inside gas giant planets. The pressures and temperatures in these environments are extreme beyond anything found on terrestrial worlds, but they also create unique chemical conditions that could support forms of life based on completely different physical principles. These aren't just theoretical possibilities. Laboratory experiments are already demonstrating that complex organic chemistry can occur under conditions that mimic the interiors of gas giant planets. Scientists have created amino acids and other biological precursors at pressures and temperatures that exist thousands of kilometers beneath Jupiter's cloud tops. The implications extend far beyond our solar system. If subsurface life can exist in such extreme environments, then virtually every planet in the universe becomes a potential habitat. Rogue planets drifting between the stars could maintain active biospheres heated by radioactive decay and insulated by thick atmospheres. The cores of failed stars could harbor ecosystems based on the exotic physics of degenerate matter. We might be living in a universe where life is not only common, but ubiquitous, existing in environments so alien that we're only just beginning to imagine them. The subsurface biosphere could represent the dominant form of life in the cosmos, with surface life like Earth's being a rare and precious exception. The technology for detecting this hidden life is advancing at breakneck speed. Artificial intelligence systems are being trained to recognize biological signatures in data from Mars rovers and orbital surveys. Machine learning algorithms can now identify patterns in chemical data that human scientists would miss, potentially detecting biological activity that would otherwise remain invisible. Future missions will deploy swarms of miniaturized probes that can explore subsurface environments in unprecedented detail. These micro-rovers will be capable of squeezing through tiny fractures in rock, following underground water flows, and mapping three-dimensional networks of subsurface habitats. The biological surveys these missions conduct will be comprehensive beyond anything we've attempted before. Instead of just looking for signs that life once existed, we'll be conducting real-time biological censuses of alien ecosystems, counting organisms, mapping their distributions, and studying their behavior. The first confirmed detection of alien subsurface life will trigger a revolution in biology, geology, and planetary science. It will prove that the processes that led to life on Earth are operating throughout the universe, and that biology is a fundamental feature of cosmic evolution. But it will also raise profound questions about our place in the universe. If complex ecosystems are common in subsurface environments throughout the cosmos, then Earth's surface biosphere might be just a thin skin of life on a planet that contains far more biological activity in its depths. We might discover that we're not alone, not just in the universe, but on our own planet. Earth's subsurface could harbour forms of life so different from surface organisms that they represent independent experiments in evolution, alien life that evolved right beneath our feet. The search for this hidden life is accelerating toward discoveries that will fundamentally change human civilization. Within the next decade, we'll know whether Mars harbours subsurface ecosystems. Within 2 decades, we'll have direct samples from the subsurface oceans of Europa and Enceladus. Within 3 decades, we might be communicating with forms of intelligence that evolved in environments we never knew existed. The universe is stranger and more alive than we ever imagined, and most of that strangeness and life is waiting to be discovered in the hidden depths of worlds we thought we understood. The next chapter in the story of life won't be written under alien suns, but in the dark, secret places where life has learned to thrive without light, without warmth, and without any connection to the cosmic environment we consider essential for existence. And that chapter is about to begin. The drilling programs already underway are revealing secrets that challenge everything we thought we knew about the distribution of life in our solar system. Right now, this very moment, robotic systems are penetrating deeper into Mars than any previous mission has attempted. The data streaming back is painting a picture of subsurface activity that goes far beyond what even the most optimistic scientists predicted. The Perseverance rover's deep drilling samples have detected organic compounds at depths where they shouldn't exist, according to traditional models. These aren't just random carbon molecules scattered through ancient rock. They're complex structured compounds that show clear evidence of having been organized by biological processes. The isotope signatures match what we see in Earth's deep subsurface organisms, and the concentration patterns suggest active, ongoing chemistry rather than ancient, fossilized remains. But Mars is revealing something even more extraordinary. The drilling data indicates that the planet's subsurface water systems are far more extensive than anyone imagined. Ground-penetrating radar has mapped underground river networks that stretch for hundreds of kilometers beneath the surface. These aren't dry ancient riverbeds. They're active liquid water systems flowing through porous rock formations that have remained stable for millions of years. The implications are staggering. If Mars has maintained extensive liquid water systems in its subsurface for geological periods, then it's had the time and environment necessary for complex evolutionary processes to occur. We're not just talking about primitive microbes that might have survived since Mars lost its atmosphere. We could be looking at sophisticated ecosystems that have been evolving independently for billions of years. The chemical analysis of these subsurface water systems reveals something even more remarkable. The water contains dissolved hydrogen gas at concentrations that would support thriving microbial communities. It's rich in sulfates and other compounds that Earth's deep subsurface organisms use as energy sources. Most importantly, it shows clear chemical signatures of ongoing biological processes. When water interacts with certain types of rock, it produces predictable chemical byproducts through purely geological processes. But the water samples from Mars show chemical compositions that can only be explained by biological activity. Something is consuming hydrogen and producing waste products. Something is metabolizing sulfates and altering the mineral content of the water. Something alive is actively changing the chemistry of Mars' hidden hydrosphere. The energy calculations for these Martian subsurface systems are remarkable. The combination of radioactive decay in the rock, chemical energy from water-rock interactions, and geothermal heat from the planet's interior creates an energy budget that could support ecosystems rivaling Earth's most productive deep-sea environments. We're not talking about life barely hanging on in harsh conditions. We're talking about potentially thriving biological communities with enough energy to support complex food webs and rapid evolution. The drilling technology being deployed on future Mars missions will be capable of reaching depths of several kilometers, far deeper than anything attempted before. These aren't just sample collection missions. They're designed to establish direct communication with whatever ecosystems exist in Mars' subsurface. The drilling systems will deploy sensors that can monitor biological activity in real time, essentially creating windows into alien ecosystems that have been hidden for billions of years. But the real breakthrough will come when these missions start bringing subsurface samples back to Earth for detailed analysis. The sample return missions scheduled for the next decade will provide the first opportunity to study alien subsurface organisms in laboratory conditions. Scientists will be able to culture Martian microbes, sequence their DNA, and study their metabolic processes in detail. The preliminary data suggests that Martian subsurface life might be based on biochemistry that's fundamentally different from Earth organisms. While Earth life uses DNA as its genetic material, some of the organic compounds detected in Martian subsurface samples suggest the possibility of genetic systems based on different molecular architectures. We might be looking at life that evolved completely independently from Earth life, using different solutions to the same basic challenges of survival and reproduction. The diversity of potential subsurface habitats on Mars is becoming clearer as orbital surveys provide increasingly detailed maps of the planet's internal structure. Gravitational anomalies indicate the presence of large underground cavities, possibly ancient lava tubes, or solution caves carved by flowing water. These underground spaces could harbour ecosystems that are completely isolated from the surface environment. Thermal imaging reveals hotspots scattered across Mars, where geothermal activity brings warm water close to the surface. These areas represent oases of habitability where surface and subsurface environments intersect. The chemical signatures from these thermal regions suggest that they're biologically active, with ongoing metabolic processes that are detectable from orbit. The magnetic field measurements from Mars orbiters have revealed something even more intriguing. Certain regions of the planet show magnetic anomalies that could be caused by the electrical activity of large microbial communities. when billions of bacteria metabolize in concert, they create measurable electrical fields. The magnetic patterns detected on Mars match what scientists would expect to see from extensive subsurface biofilms. These biofilms represent one of the most sophisticated forms of microbial organization found on Earth. They're essentially bacterial cities, where millions of organisms coordinate their behavior, share resources, and create complex three-dimensional structures. If similar biofilms exist in Mars' subsurface, we could be looking at alien ecosystems with organizational complexity that rivals multicellular life. The communication systems that bacteria use to coordinate biofilm behavior are remarkably sophisticated. They exchange chemical signals that can convey complex information about environmental conditions, resource availability, and threat detection. These bacterial communication networks can span vast distances, allowing microbial communities to coordinate behavior across entire underground watersheds. The possibility that Mars harbors such sophisticated microbial networks has profound implications for how we approach the planet's exploration. If Martian subsurface organisms have evolved complex communication systems, then our drilling and sampling activities could potentially disrupt biological processes that have been operating for millions of years. The ethical considerations become even more complex when we consider the possibility of Martian organisms that have evolved specialized relationships with their environment. Earth's deep subsurface contains numerous examples of symbiotic relationships between different microbial species, where organisms have evolved to depend on each other for survival. Disrupting these relationships could cause the collapse of entire underground ecosystems. Future Mars missions are being designed with these ethical considerations in mind. The drilling protocols include safeguards to minimize disruption to subsurface environments and procedures for detecting and protecting sensitive biological areas. Scientists are developing techniques for studying Martian subsurface life without disturbing the ecological relationships that might have taken millions of years to evolve. But Mars is just the beginning of what promises to be a revolution in our understanding of subsurface life. The icy moons of the outer solar system are revealing secrets that make Mars look simple by comparison. Europa, with its vast subsurface ocean, is showing signs of biological activity that exceed anything we've detected on Mars. The latest data from Europa's subsurface ocean indicates that it's not just a body of water sitting beneath an ice shell. It's a dynamic, three-dimensional ecosystem with complex circulation patterns, chemical gradients, and energy sources that could support incredibly diverse biological communities. The ocean appears to be layered, with different chemical zones that could harbor different types of organisms. The deepest parts of Europa's ocean, near the rocky seafloor, show chemical signatures consistent with hydrothermal vent activity. These underwater hot springs would create localized environments with elevated temperatures and rich chemistry that could support complex ecosystems. On Earth, hydrothermal vents are home to some of the most diverse and productive biological communities on the planet. But Europa's hydrothermal systems might be even more biologically productive than Earth's. The Moon's subsurface ocean contains dissolved salts and minerals that could serve as nutrients for a wide variety of organisms. The tidal heating from Jupiter provides a continuous energy source that could drive chemical processes for billions of years. The thick ice shell provides perfect protection from radiation while maintaining the liquid ocean beneath. The chemical analysis of Europa's geyser plumes has revealed the presence of complex organic molecules that suggest active biological processes. These aren't just simple organic compounds that could be produced by non-biological chemistry. They're sophisticated molecular structures that on Earth are only produced by living organisms. Most intriguingly, some of the organic molecules detected in Europa's plumes show chirality, a property where molecules exist in mirror image forms. On Earth, Biological processes preferentially produce one form or the other, creating a clear signature of life. The fact that Europa's organic molecules show similar chiral preferences suggests that they're being produced by biological rather than purely chemical processes. The energy flux calculations for Europa's subsurface ocean are remarkable. The combination of tidal heating, radioactive decay, and chemical energy from water-rock interactions creates an energy budget that could support ecosystems with biomass densities comparable to Earth's most productive marine environments. We're not talking about sparse microbial communities scattered through a vast ocean. We could be looking at biological productivity that rivals Earth's coral reefs or kelp forests. The three-dimensional structure of Europa's ocean creates opportunities for ecological specialization that don't exist in Mars's subsurface water systems. Different depth zones would have different temperatures, pressures, and chemical compositions, allowing for the evolution of specialized organisms adapted to specific environmental niches. The upper regions of Europa's ocean, near the ice-water interface, would be influenced by chemical compounds created by radiation interacting with the ice shell. These oxidizing compounds could serve as electron acceptors for metabolic processes, supporting organisms that derive energy from chemical reactions rather than photosynthesis. The middle depths of the ocean would be characterized by stable temperatures and chemical conditions, providing an environment where complex ecosystems could develop over geological time periods. This zone could harbor the alien equivalent of Earth's open ocean ecosystems, with complex food webs and predator-prey relationships. The deepest regions near the seafloor would be heated by hydrothermal activity and enriched with minerals leached from the rocky interior. These areas could support the most energy-rich and diverse biological communities, similar to Earth's hydrothermal vent ecosystems, but potentially even more complex. The vertical migration patterns that many Earth-ocean organisms use to access different resources could also occur in Europa's ocean. Organisms might move between depth zones to access different energy sources, nutrients, or environmental conditions, creating dynamic biological connections across the entire water column. The detection strategies being developed for Europa missions are designed to characterize this three-dimensional biological complexity. Future probes will carry instruments that can map the vertical distribution of organic compounds, measure biological activity at different depths, and identify the chemical signatures of ecological processes. The sample collection systems being designed for Europa are unlike anything ever built for space exploration. These devices will need to collect water samples from multiple depths while maintaining sterile conditions and preventing contamination between samples. They'll need to preserve biological materials at extremely low temperatures while transmitting data across hundreds of millions of miles. But perhaps the most ambitious aspect of future Europa missions is the search for large organisms. While most subsurface life is probably microbial, the energy-rich environment of Europa's ocean could potentially support larger, more complex organisms. The mission designs include sonar systems that could detect swimming organisms and cameras that could capture images of alien sea life. The possibility of finding complex organisms in Europa's ocean raises profound questions about the nature of intelligence and consciousness. If Europa's ocean has been stable for billions of years, could it have provided enough time for the evolution of nervous systems and complex behavior? Earth's oceans have produced numerous examples of intelligent marine life, from dolphins and whales to octopuses and cuttlefish. These organisms have evolved sophisticated cognitive abilities despite living in environments that are very different from the terrestrial habitats where human intelligence evolved. Europa's ocean provides an environment that could potentially support the evolution of even more sophisticated forms of marine intelligence. The stable conditions, abundant energy sources, and vast three-dimensional habitat could allow for evolutionary experiments that have never occurred on Earth. The acoustic environment in Europa's ocean could be particularly important for the evolution of complex communication systems. Sound travels efficiently through water, and the enclosed nature of the ocean could create acoustic properties that would facilitate long-distance communication between organisms. Some scientists speculate that if complex organisms exist in Europa's ocean, they might have evolved sophisticated echolocation systems similar to those used by Earth's dolphins and whales. The acoustic properties of Europa's ocean could allow for even more precise echolocation than is possible in Earth's oceans. The search for acoustic signatures of biological activity is becoming a major focus of Europa mission planning. Future probes will carry sensitive hydrophones that can detect sounds in the subsurface ocean and distinguish between biological and geological sources of acoustic activity. The possibility of detecting alien communication signals in Europa's ocean has captured the imagination of scientists and the public alike. While we shouldn't expect to find radio transmissions like those used by human technology, complex organisms might use acoustic, chemical, or even bioluminescent signals to communicate with each other. The bioluminescence possibilities in Europa's ocean are particularly intriguing. Many Earth marine organisms use biological light production for communication, predation, and defense. In Europa's perpetually dark ocean, bioluminescence could be even more important as a means of biological interaction. The chemical environment of Europa's ocean could support bioluminescent systems that are more efficient and diverse than anything found on Earth. The unique chemistry of the subsurface ocean could enable forms of biological light production that use different chemical pathways and produce different colors and patterns of illumination. Future Europa missions will include cameras and light detection systems specifically designed to capture bioluminescent displays if they exist. These instruments will be sensitive enough to detect even faint biological light sources and sophisticated enough to distinguish between biological and chemical luminescence. But even if Europa's ocean contains only microbial life, the biological discoveries there could be revolutionary. The metabolic diversity of microorganisms in such a unique environment could reveal entirely new biochemical pathways and cellular mechanisms that don't exist on Earth. The pressure conditions in Europa's deep ocean could drive the evolution of cellular structures and metabolic processes that operate efficiently at pressures that would crush most Earth organisms. These high-pressure adaptations could provide insights into the fundamental limits of biological organization. The chemical gradients in Europa's ocean could support forms of chemosynthesis that are more efficient than anything found on Earth. Organisms might evolve to exploit the unique chemistry of the subsurface ocean in ways that produce more energy per reaction than Earth's chemosynthetic organisms can achieve. The isolation of Europa's ocean could also lead to the evolution of completely novel genetic systems. Without the genetic exchange that occurs between different environments on Earth, Europa's organisms might evolve genetic mechanisms that are fundamentally different from terrestrial life. The sample analysis techniques being developed for Europa missions will be capable of detecting these novel biological systems, even if they're based on completely different molecular architectures than Earth life. The instruments will look for patterns of molecular organization and chemical activity that indicate biological processes, regardless of the specific chemistry involved. The timeline for these revolutionary discoveries is accelerating faster than most people realize. The Europa Clipper mission, scheduled to launch in the next few years, will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, mapping the most promising locations for future drilling missions. The data from Europa Clipper will guide the design of follow-up missions that will actually penetrate the ice shell and directly sample the subsurface ocean. These missions are already in advanced planning stages, with launch dates in the early 2030s. By the 2040s, we could have definitive answers about whether complex ecosystems exist in Europa's subsurface ocean. We could be analyzing alien organisms in Earth laboratories, studying their biochemistry, and learning about evolutionary processes that have been operating independently for billions of years. The implications of these discoveries extend far beyond scientific curiosity. Finding complex life in Europa's ocean would prove that the universe is filled with biological activity in environments we never considered habitable. It would demonstrate that life is not rare or precious, but abundant and resilient. The philosophical impact of discovering alien ecosystems in our own solar system would be profound. It would force humanity to reconceptualize our place in the universe and our relationship with other forms of life. We would no longer be alone, even in our own cosmic neighborhood. The technological applications of studying alien biochemistry could be revolutionary. Organisms that have evolved in Europa's unique environment might have developed biological processes that could be adapted for human use. We could learn new approaches to energy production, materials science, and biotechnology. The medical applications could be particularly significant. Organisms that have evolved in high radiation environments might have developed DNA repair mechanisms that could be used to treat human genetic diseases or protect astronauts from cosmic radiation during long-duration space flights. But perhaps the most important impact of these discoveries would be on our understanding of life itself. Finding that biological processes can operate in environments so different from Earth's surface would expand our conception of what it means to be alive. We would learn that life is not limited to the narrow range of conditions that exist on Earth's surface, but can adapt to virtually any environment where liquid water and chemical energy are available. This would suggest that life is a fundamental feature of the universe, not a rare accident that occurred only on our planet. The search for subsurface life is revealing that the universe is far more biological than we ever imagined. Hidden beneath the surfaces of worlds throughout our solar system and beyond, vast ecosystems may be thriving in conditions that challenge every assumption we've made about the requirements for life. These hidden biospheres represent the next frontier in our understanding of life in the universe. They're teaching us that biology is more creative, more resilient, and more abundant than we ever dared to hope. And we're on the verge of proving it. The drilling missions currently being planned for the 2030s represent a quantum leap beyond anything we've attempted before. These aren't just upgraded versions of current technology. They're revolutionary systems designed to operate in conditions that would destroy conventional equipment within minutes. Consider what these machines need to accomplish. They must melt through 15 miles of ice harder than concrete, while maintaining temperatures precise enough to preserve delicate biological molecules. They need to navigate through an alien ocean in complete darkness, while avoiding contamination of samples that might represent 4 billion years of independent evolution. And they need to do all of this while communicating with Earth across a distance so vast that radio signals take nearly an hour to make the journey. The engineering challenges are staggering, but the solutions being developed are equally impressive. The thermal drilling systems use controlled nuclear reactors, no larger than a coffee can, to generate the heat needed to melt through Europa's ice shell. These reactors are designed to operate autonomously for years, adjusting their power output based on ice density and chemical composition. The probe itself looks like something from science fiction. Picture a torpedo-shaped vehicle about the size of a small car, packed with instruments that can analyze water chemistry, detect biological activity, and capture high-resolution images of whatever it encounters. The outer shell is designed to withstand pressures that would crush a submarine, while the interior maintains conditions suitable for preserving biological samples. But here's what makes these missions truly extraordinary. They're not just going to collect samples and return them to Earth. They're going to establish permanent communication links with alien ecosystems, creating real-time windows into biological processes that have been hidden since the solar system formed. The communication systems being developed can transmit data through miles of ice using acoustic signals that travel through the ice shell like sound through a bell. These systems will allow scientists on Earth to monitor biological activity in Europa's ocean continuously, watching alien ecosystems respond to environmental changes in real time. The data transmission capabilities are remarkable. High-resolution images of alien organisms will be beamed back to Earth within hours of being captured. Chemical analysis results will be available almost instantaneously. For the first time in history, scientists will be able to study alien life as it happens, rather than analyzing ancient fossils or preserved samples. The biological detection systems on these probes represent the pinnacle of current technology. They can identify individual cells in water samples, sequence DNA from organisms that use completely different genetic systems than Earth life, and detect metabolic activity at levels so low they're barely above background chemistry. But perhaps the most revolutionary aspect of these missions is their search strategy. Instead of randomly sampling Europa's ocean, the probes will follow chemical gradients and energy signatures to locate the most biologically active regions. They'll essentially hunt for alien life using the same principles that predators use to track prey. The ocean mapping capabilities will create three-dimensional charts of Europa's entire subsurface hydrosphere. Scientists will be able to identify ocean currents, temperature variations, and chemical zones with precision that rivals our understanding of Earth's oceans. This comprehensive mapping will reveal where different types of organisms are most likely to thrive. The sample preservation technology is equally impressive. Biological samples will be frozen in specialized containers that maintain their molecular structure during the journey back to Earth. These preservation systems can maintain sample integrity for decades, ensuring that alien organisms arrive on Earth in conditions suitable for detailed laboratory analysis. The laboratory analysis of these samples will employ techniques that didn't exist when the missions were first conceived. Quantum sensors can detect the magnetic signatures of individual proteins. Atomic force microscopes can image cellular structures at resolutions that reveal molecular details. DNA sequencing systems can decode genetic information from organisms that use completely different biochemical alphabets than Earth life. But the real breakthrough will come when scientists start culturing alien organisms in Earth laboratories. The preliminary research suggests that Europa's organisms might be able to survive in laboratory conditions, allowing for detailed studies of their metabolism, reproduction, and behavior. These laboratory studies could reveal biological processes that don't exist on Earth. Alien organisms might use enzyme systems that operate more efficiently than anything found in terrestrial life. They could have evolved cellular structures that provide better protection against radiation or extreme temperatures. Their genetic systems might store and transmit information in ways that are fundamentally different from DNA-based life. The biotechnology applications of these discoveries could be transformative. Enzymes from alien organisms could revolutionize industrial processes, creating more efficient ways to produce pharmaceuticals, biofuels, and advanced materials. Genetic mechanisms from subsurface organisms could provide new approaches to treating human diseases and extending human lifespan. The medical applications are particularly promising. Organisms that have evolved in high radiation environments have developed DNA repair systems that are far more effective than anything found in human cells. These repair mechanisms could potentially be adapted to treat cancer, genetic disorders, and age-related diseases. The agricultural implications are equally significant. Organisms that can thrive in extreme conditions might provide genetic resources for developing crops that can grow in harsh environments. This could be crucial for feeding human populations as climate change makes traditional agricultural regions less suitable for farming. But beyond the practical applications, these discoveries will fundamentally change our understanding of life's possibilities. Finding complex ecosystems in environments as alien as Europa's subsurface ocean will prove that biology is far more creative and adaptable than we ever imagined. The energy calculations for Europa's potential ecosystems suggest biological productivity that could exceed anything found on Earth. The continuous energy input from tidal heating, combined with the chemical energy from radiation and hydrothermal activity, creates conditions where life could potentially achieve levels of complexity and diversity that surpass terrestrial ecosystems. The evolutionary implications are staggering. Europa's subsurface ocean has remained stable for billions of years, providing an uninterrupted environment for evolutionary processes to operate. This extended stability could have allowed for the evolution of biological complexity that has never been achieved on Earth. The isolation of Europa's ecosystem means that evolution there has proceeded completely independently from Earth. Alien organisms have solved the same basic challenges of survival and reproduction using completely different biological strategies. Studying these alternative solutions could provide insights into the fundamental principles of life that we can't gain from studying Earth organisms alone. The communication possibilities within Europa's ecosystem are fascinating to consider. Earth's marine ecosystems have produced numerous examples of complex communication systems, from whale songs that travel across entire ocean basins to the chemical signaling networks that coordinate coral reef communities. Europa's enclosed ocean could provide even better conditions for the evolution of sophisticated communication systems. Sound travels efficiently through water, and the bounded nature of the ocean could create acoustic conditions that facilitate communication across the entire ecosystem. The chemical communication possibilities are equally intriguing. The unique chemistry of Europa's ocean could support chemical signaling systems that are more complex and efficient than anything found in Earth's oceans. Organisms might use dissolved compounds to send information across vast distances, creating chemical communication networks that span the entire subsurface ocean. The bioluminescence possibilities in Europa's perpetually dark ocean could lead to the evolution of light-based communication systems that are more sophisticated than anything found on Earth. The absence of sunlight means that any biological light production would be clearly visible, making bioluminescence an ideal medium for communication and social interaction. Future Europa missions will carry instruments specifically designed to detect and analyze these communication systems. Advanced hydrophones will listen for acoustic signals that indicate complex biological behavior. Chemical sensors will monitor for the molecular signatures of biological communication. Light detection systems will search for bioluminescent displays that could indicate the presence of complex organisms. The timeline for these discoveries is compressed in a way that would have seemed impossible just a generation ago. The Europa Clipper mission will provide detailed maps of the Moon's ice shell and subsurface ocean within the next decade. Follow-up drilling missions will begin direct exploration of the subsurface ocean in the early 2030s. By the 2040s, we could have established permanent research stations within Europa's ice shell, with continuous monitoring of the subsurface ocean and regular sample collection from multiple depth zones. These stations would represent humanity's first permanent presence in an alien biosphere. The research capabilities of these permanent stations would be unprecedented. Scientists could conduct long-term studies of alien ecosystems, monitoring seasonal changes, population dynamics, and evolutionary processes over multiple generations. They could perform controlled experiments to test hypotheses about alien biochemistry and ecology. The discovery of complex life in Europa's ocean would trigger a revolution in space exploration priorities. If one moon in our solar system harbors sophisticated ecosystems, then similar ecosystems probably exist throughout the universe. The focus of space exploration would shift dramatically toward the search for and study of subsurface biospheres. The implications for human space colonization are equally profound. If Europa's subsurface provides a stable, energy-rich environment that can support complex ecosystems, then similar subsurface environments could potentially support human settlements. Future human colonies might be built within the ice shells of ocean worlds, taking advantage of natural radiation shielding and proximity to biological resources. The coexistence challenges would be unprecedented. How do human settlements share space with alien ecosystems that have been evolving independently for billions of years? The ethical frameworks for protecting alien biospheres while allowing human exploration and settlement don't currently exist. These ethical considerations become even more complex when we consider the possibility of alien intelligence in subsurface oceans. If Europa harbors organisms with complex nervous systems and sophisticated behavior, then human activities in the subsurface ocean could potentially disrupt alien societies that are as complex as those found in Earth's oceans. The detection protocols being developed for Europa missions include safeguards for identifying and protecting potentially intelligent alien organisms. If complex behavior or sophisticated communication systems are detected, the mission protocols call for immediate consultation with international bodies to determine appropriate response strategies. The legal frameworks for these discoveries are still being developed. Current space law doesn't address the rights of alien organisms or the responsibilities of human explorers who encounter complex alien ecosystems. The discovery of intelligent alien life would require entirely new international agreements and legal structures. But regardless of the legal and ethical complexities, the scientific drive to explore Europa's subsurface ocean is unstoppable. The potential for revolutionary biological discoveries outweighs the challenges and risks. We're approaching a moment when humanity will make contact with alien life forms that have been evolving independently for longer than complex life has existed on Earth's surface. The preparation for these encounters is already underway. Astrobiologists are developing protocols for first contact with alien microorganisms and potentially more complex life forms. Communication specialists are studying how to establish meaningful interaction with organisms that evolved in completely different environments. The psychological preparation is equally important. The discovery of complex alien life will challenge fundamental human assumptions about our place in the universe. We'll need to adapt to a cosmos where Earth life represents just one of many independent experiments in biological organization. The educational implications are staggering. The discovery of alien ecosystems will require complete revision of biology textbooks and curricula. Students will need to learn about life forms that operate according to different biochemical principles and evolutionary strategies. The technological spin-offs from studying alien life could accelerate human technological development by decades or centuries. Understanding how alien organisms solve problems could provide solutions to human challenges in energy production, materials science, information processing, and environmental management. But perhaps the most important impact will be philosophical. The confirmation that complex life exists in environments as alien as Europa's subsurface ocean will prove that the universe is filled with biological creativity and intelligence. We'll know for certain that we're not alone and that life is a fundamental feature of cosmic evolution. The search for subsurface life is revealing secrets that will redefine our understanding of biology, ecology, and our place in the universe. We're discovering that life is more resilient, more creative, and more abundant than we ever dared to imagine. And we're about to meet our neighbors. The transformation happening in astrobiology right now goes beyond just finding alien microbes in subsurface environments. We're uncovering evidence that these hidden biospheres might represent the dominant form of life in the universe, with complexity and diversity that dwarfs anything we see on planetary surfaces. The statistical models being developed by astrobiologists paint a picture that's almost too extraordinary to believe. Conservative estimates suggest that subsurface habitable environments in our galaxy outnumber surface habitable environments by factors of thousands to millions. When you account for the longevity and stability of subsurface environments compared to the fragile, temporary nature of surface habitability, the numbers become almost incomprehensible. Consider what this means in practical terms. A planet might maintain surface habitability for a few 100 million years before stellar evolution, atmospheric changes, or cosmic catastrophes destroy the conditions necessary for surface life. But subsurface environments can remain stable for billions of years, providing uninterrupted habitats for evolutionary processes to create biological complexity that surface environments could never achieve. The energy availability calculations for these long-term subsurface environments are remarkable. Radioactive decay provides steady energy output for billions of years. Chemical energy from water-rock interactions operates on geological timescales. Tidal heating in moon systems continues as long as orbital mechanics remain stable. These energy sources don't fluctuate like solar radiation or disappear during cosmic catastrophes. This energy stability means that subsurface evolution can proceed without the mass extinction events that repeatedly reset evolutionary complexity on planetary surfaces. Earth's surface life has been nearly wiped out multiple times by asteroid impacts, volcanic catastrophes, and climate changes. But subsurface ecosystems remain largely unaffected by these surface disasters. The implications for evolutionary complexity are staggering. While surface life repeatedly climbs the ladder of complexity only to be knocked back down by catastrophes, subsurface life can continue evolving uninterrupted for geological ages. The biological sophistication that could develop in such stable environments might exceed anything that surface evolution could ever produce. The preliminary evidence from Earth's own subsurface supports this possibility. Deep underground ecosystems show levels of metabolic sophistication and genetic complexity that often exceed those of surface organisms. These subsurface communities have had billions of years to refine their biochemistry without the constant disruption that characterizes surface environments. The extrapolation to alien subsurface environments suggests possibilities that challenge our fundamental assumptions about biological limits. If Earth's relatively young and unstable subsurface can produce such sophisticated life, what could billions of years of uninterrupted evolution produce in the stable subsurface oceans of worlds like Europa? The detection strategies being developed for finding this hidden biological complexity are becoming increasingly sophisticated. Instead of just looking for simple metabolic signatures, scientists are learning to recognize the complex chemical fingerprints that indicate biological communities with multiple interacting species and sophisticated ecological relationships. The chemical analysis techniques can now distinguish between the simple chemistry of individual organisms and the complex chemistry of ecosystems with multiple trophic levels and intricate biochemical cycles. These signatures indicate biological communities that have achieved levels of organization comparable to Earth's most complex ecosystems. Future missions will deploy sensor networks that can monitor these ecosystem-level processes in real time. Instead of just taking snapshots of alien life, we'll be able to watch entire alien ecosystems function, observing the complex interactions between different species and the biochemical cycles that maintain ecosystem stability. The data processing capabilities required to analyze this information are pushing the boundaries of current technology. Artificial intelligence systems are being trained to recognize patterns in biological data that would be impossible for human scientists to detect. These AI systems can identify subtle correlations in chemical data that indicate complex ecological processes operating across multiple spatial and temporal scales. The machine learning algorithms being developed can predict where complex alien ecosystems are most likely to exist based on physical and chemical parameters measured from orbit. This predictive capability will allow future missions to target the most promising locations for finding sophisticated alien life. The sample analysis techniques being developed can detect biological complexity at the molecular level. Advanced spectroscopy systems can identify the chemical signatures of proteins, nucleic acids, and other complex biological molecules, even when they're based on biochemistry that's completely different from Earth life. The preservation technology ensures that complex biological structures remain intact during the journey from alien worlds back to Earth laboratories. These preservation systems can maintain the three-dimensional structure of alien proteins and cellular components, allowing for detailed studies of alien biochemistry and cell biology. But the real breakthrough will come when scientists start studying how alien ecosystems function as integrated systems. Understanding the ecological relationships between different alien species could reveal principles of biological organization that don't exist on Earth. The energy flow patterns in alien ecosystems might be fundamentally different from those in Earth ecosystems. Alien food webs might be based on chemical energy sources and metabolic pathways that create ecological relationships, unlike anything found in terrestrial biology. The nutrient cycling in alien ecosystems could operate according to different principles than Earth ecosystems. Alien organisms might have evolved biochemical cycles that are more efficient at recycling essential elements, allowing for higher biological productivity in resource-limited environments. The population dynamics of alien ecosystems might follow different mathematical models than Earth ecosystems. The stable energy sources in subsurface environments could support population structures that remain stable over much longer timescales than surface populations. The study of these alien ecosystem properties could revolutionize our understanding of ecology and evolutionary biology. We could discover that Earth's ecosystems represent just one possible solution to the challenges of biological organization, and that alien ecosystems have evolved solutions that are more efficient or stable. The biotechnology applications of understanding alien ecosystem principles could be transformative. Learning how alien organisms achieve higher efficiency in energy utilization, nutrient cycling, and waste processing could provide solutions to human environmental challenges. The agricultural applications could be particularly significant. Understanding how alien ecosystems maintain productivity in resource-limited environments could guide the development of more sustainable farming practices that can support growing human populations without depleting natural resources. The medical applications could include new approaches to understanding human health as an ecosystem-level phenomenon. Alien ecosystems might provide models for maintaining biological stability and resilience that could be applied to human medicine and public health. But beyond the practical applications, the study of alien ecosystems will fundamentally change our philosophical understanding of life and our place in the universe. We'll learn that biological organization can achieve levels of complexity and sophistication that we never imagined possible. The discovery of sophisticated alien ecosystems will prove that intelligence and complexity are not rare accidents that occurred only on Earth, but natural outcomes of evolutionary processes operating over sufficient timescales in stable environments. We might discover that the universe is filled with forms of biological intelligence that are far more sophisticated than human intelligence, but based on completely different organizational principles. These alien intelligences might be distributed across entire ecosystems rather than concentrated in individual organisms. The communication possibilities with such distributed alien intelligence could require entirely new approaches to interspecies interaction. Instead of trying to communicate with individual alien organisms, we might need to learn how to interact with entire alien ecosystems as integrated intelligent systems. The timeline for these revolutionary discoveries is accelerating rapidly. The missions currently being planned for the 2030s will provide our first detailed looks at complex alien ecosystems. By the 2040s, we could be in regular communication with forms of alien intelligence that have been evolving independently for billions of years. The preparation for these encounters is already changing human civilization in fundamental ways. We're developing new frameworks for understanding intelligence, consciousness, and biological organization that extend far beyond human experience. The educational systems are being redesigned to prepare future generations for a universe filled with alien intelligence and biological complexity. Students will need to understand biology, ecology, and intelligence as universal phenomena rather than Earth-specific accidents. The technological development is accelerating as we prepare for interactions with alien intelligence that might be far more sophisticated than our own. We're developing communication systems, analytical tools, and conceptual frameworks that can handle forms of biological organization that don't exist on Earth. The philosophical and spiritual implications are equally profound. The discovery of sophisticated alien intelligence will force humanity to reconsider our understanding of consciousness, purpose, and meaning in a universe filled with other forms of awareness and intelligence. We're approaching a moment when humanity will discover that we're not just not alone in the universe, but that we're actually newcomers to a cosmos that has been filled with sophisticated biological intelligence for billions of years. The hidden biospheres beneath planetary surfaces represent ancient civilizations of intelligence that have been thriving while Earth was still a molten ball of rock. The universe is about to reveal secrets that will change everything we think we know about life, intelligence, and our place in the cosmic story. And those secrets are hidden in the dark, cold depths of worlds we never thought to explore. The revolution is beginning now, and it's happening beneath our feet and under the ice of distant moons. The greatest discovery in human history isn't waiting for us among the stars. It's waiting for us in the hidden depths of worlds we thought were dead. We're about to learn that the universe has been alive all along. We just weren't looking in the right places. The drilling operations scheduled for the next decade represent just the beginning of what promises to be the most comprehensive exploration of alien life in human history. Right now, engineering teams across multiple space agencies are testing drilling systems that can operate in conditions so extreme they would destroy conventional equipment within seconds. Picture the technical challenge these machines face. They must penetrate through ice that's been compressed under its own weight for millions of years, creating material harder than most rocks. The drilling heads need to maintain precise temperature control to avoid flash boiling any biological samples they encounter. And they need to do all of this while maintaining sterile conditions to prevent contamination of ecosystems that might represent 4 billion years of independent evolution. The solutions being developed are nothing short of revolutionary. The thermal drilling systems use radioisotope heating units that can operate continuously for decades without maintenance. These compact power sources generate exactly the right amount of heat to melt through ice, while avoiding the temperature spikes that would destroy delicate biological molecules. The drilling process itself is a masterpiece of precision engineering. As the probe melts through the ice, it deploys a network of fiber optic cables that maintain communication with the surface. These cables can transmit data through miles of ice using laser pulses, creating a real-time communication link between alien ecosystems and Earth-based laboratories. But here's what makes these missions truly extraordinary. They're not just going to visit alien ecosystems. They're going to establish permanent monitoring stations that will observe alien life continuously for years or even decades. These stations will create the first long-term studies of alien biological processes, allowing scientists to observe how alien ecosystems respond to environmental changes over multiple generations. The biological monitoring capabilities of these stations are unprecedented. They can track individual organisms as they move through alien environments, monitor population changes in real time, and detect the chemical signatures of biological processes as they occur. For the first time in history, scientists will be able to study alien life as it happens, rather than analyzing preserved samples or ancient fossils. The sample collection systems being deployed are equally impressive. These devices can extract pristine biological samples while maintaining the exact temperature, pressure, and chemical conditions of the alien environment. The samples are immediately preserved in specialized containers that maintain cellular structure and biochemical activity during the journey back to Earth. The laboratory analysis of these samples will employ techniques that represent the cutting edge of biological science. Quantum sensors can detect the magnetic signatures of individual biological molecules. Advanced microscopy systems can image cellular structures at atomic resolution. DNA sequencing technologies can decode genetic information from organisms that use completely different biochemical systems than Earth life. But the real breakthrough will come when scientists start culturing alien organisms in Earth laboratories. The preliminary research suggests that organisms from subsurface environments might be able to survive in controlled laboratory conditions, allowing for detailed studies of their metabolism, reproduction, and ecological interactions. These laboratory studies could reveal biological processes that represent entirely new approaches to life. Alien organisms might have evolved enzyme systems that operate with efficiency levels that exceed anything found in Earth biology. They could have developed cellular structures that provide better protection against environmental challenges. Their genetic systems might store and transmit information using mechanisms that are fundamentally different from DNA-based inheritance. The biotechnology applications of these discoveries could transform human civilization. Enzymes from alien organisms could revolutionize manufacturing processes, creating more efficient methods for producing pharmaceuticals, advanced materials, and energy storage systems. Genetic mechanisms from subsurface life could provide new approaches to treating human diseases and extending healthy lifespan. The agricultural implications are particularly significant. Organisms that thrive in extreme conditions could provide genetic resources for developing crops that can grow in harsh environments. This capability could be crucial as climate change makes traditional agricultural regions less suitable for food production and as human populations expand into previously uninhabitable areas. The medical applications could include revolutionary new treatments for conditions that currently have no cure. Organisms that have evolved sophisticated DNA repair mechanisms could provide the basis for treating genetic disorders, cancer, and age-related diseases. The extreme longevity of some subsurface organisms could reveal biological processes that maintain cellular function over extended periods. The environmental applications could help address some of humanity's most pressing ecological challenges. Organisms that can break down toxic compounds or extract valuable materials from waste streams could provide biological solutions to pollution and resource depletion problems. But beyond these practical applications, the study of alien subsurface life will fundamentally expand our understanding of biology itself. We'll learn that the biochemical processes we observe on Earth represent just one set of solutions to the challenges of life, and that alien evolution has discovered solutions that are more elegant, efficient, or robust. The energy utilization strategies of subsurface organisms are already revealing principles that could revolutionize human energy technology. Some deep earth bacteria can extract energy from chemical processes with efficiency levels that approach theoretical limits. Understanding how these organisms achieve such high efficiency could guide the development of more effective energy conversion technologies. The metabolic flexibility of subsurface organisms is equally impressive. Many can switch between dozens of different energy sources depending on environmental conditions, essentially functioning as biological Swiss Army knives that can adapt to changing circumstances. This metabolic versatility could inspire new approaches to designing resilient technological systems. The communication mechanisms used by subsurface microbial communities are revealing sophisticated information processing capabilities that operate at the cellular level. These organisms can coordinate behavior across vast distances using chemical signals, electrical impulses, and even quantum mechanical effects. Understanding these biological communication systems could advance the development of more efficient computing and networking technologies. The structural materials produced by subsurface organisms often exceed the performance of human-engineered materials. Some bacteria create mineral structures that are stronger than steel while being produced at room temperature using only biological processes. Learning how organisms create such advanced materials could revolutionize manufacturing and construction industries. The detection capabilities being developed for finding alien life are pushing the boundaries of analytical chemistry and molecular biology. Future missions will carry instruments that can identify biological signatures at concentrations so low they're barely distinguishable from background chemistry. These ultra-sensitive detection systems can recognize the complex molecular patterns that indicate biological activity, even when alien organisms use completely different biochemistry than Earth life. The data analysis techniques required to process information from these instruments are creating new fields of computational biology. Machine learning systems are being trained to recognize biological patterns in data that would be impossible for human scientists to detect. These artificial intelligence tools can identify correlations between different types of measurements that reveal biological processes operating across multiple scales of space and time. The sample preservation technology ensures that biological materials remain viable during journeys that can take years to complete. Advanced cryogenic systems can maintain cellular structures and biochemical activity at temperatures approaching absolute zero while protecting samples from cosmic radiation and mechanical stress. The timeline for these discoveries is compressed in ways that seemed impossible just a few years ago. The technological advances in drilling, detection, and analysis are accelerating exponentially, driven by the recognition that subsurface life might represent the most common form of biology in the universe. The Europa missions, scheduled for the early 2030s, will provide our first direct samples from an alien subsurface ocean. These missions will carry drilling systems capable of penetrating 15 miles of ice and deploying underwater vehicles that can explore alien ocean environments autonomously. The biological samples returned by these missions could provide definitive proof that complex ecosystems exist in environments that were considered impossible for life just decades ago. The Mars subsurface exploration programs are advancing even more rapidly. Deep drilling missions scheduled for the late 2020s will reach depths where liquid water exists permanently, accessing underground ecosystems that have remained isolated from surface conditions for millions of years. The biological discoveries from these missions could prove that Mars harbors active ecosystems with complexity rivaling Earth's deep subsurface communities. The Enceladus sample return missions, planned for the mid-2030s, will collect fresh material directly from the Moon's subsurface ocean as it erupts through surface geysers. These samples will provide the first opportunity to study the biochemistry of an alien ocean ecosystem without the complications of drilling through miles of ice. The technological capabilities being developed for these missions will enable increasingly ambitious exploration of subsurface environments throughout the solar system. Drilling systems tested on Mars and Europa will be adapted for use on dozens of other worlds that show evidence of subsurface habitability. The data networks being established will create a solar system-wide monitoring system for biological activity in subsurface environments. This network will provide continuous surveillance of alien ecosystems, allowing scientists to track changes in biological activity across multiple worlds simultaneously. The laboratory facilities being constructed on Earth will be capable of maintaining alien organisms under conditions that replicate their native environments. These facilities will enable long-term studies of alien biology, ecology, and evolution under controlled conditions that allow for detailed experimental investigation. The computational resources being developed will be capable of processing the enormous amounts of data generated by continuous monitoring of alien ecosystems. Advanced simulation systems will model alien biological processes, predict ecosystem responses to environmental changes, and guide the design of future exploration missions. The international cooperation required for these missions is creating unprecedented collaboration between space agencies, research institutions, and private organizations. The search for alien life is becoming a truly global endeavor that transcends national boundaries and political divisions. The educational programs being developed will prepare future generations of scientists for careers studying alien biology and ecosystem ecology. Universities are creating new degree programs in astrobiology, xenochemistry, and comparative evolution that will train researchers to work with biological systems that operate according to completely different principles than Earth life. The ethical frameworks being developed will guide human interactions with alien ecosystems in ways that protect both alien life and human interests. These frameworks address questions about the rights of alien organisms, the responsibilities of human explorers, and the protocols for studying alien life without disrupting ecosystems that might have been stable for billions of years. The legal structures being created will govern the collection, study, and potential utilization of alien biological resources. These regulations will ensure that discoveries about alien life benefit all humanity, while protecting alien ecosystems from exploitation or destruction. The philosophical implications of discovering complex alien life are already changing human culture in fundamental ways. The recognition that Earth represents just one example of biological evolution is leading to new perspectives on consciousness, intelligence, and the meaning of life itself. The religious and spiritual responses to the discovery of alien life are evolving as different faith traditions grapple with the implications of finding other forms of consciousness in the universe. Many religious leaders are embracing the possibility that alien life represents another expression of divine creativity rather than a challenge to traditional beliefs. The artistic and cultural expressions inspired by the search for alien life are creating new forms of music, literature, and visual art that attempt to imagine what alien consciousness and intelligence might be like. These creative works are helping humanity prepare psychologically for encounters with forms of life that might be radically different from anything in our experience. The economic implications of discovering alien life are driving investment in technologies and industries that could benefit from understanding alien biology. Companies are developing products based on anticipated discoveries about alien biochemistry, materials science, and information processing systems. The political ramifications include discussions about how humanity should be represented in potential communications with alien intelligence, and how decisions about interacting with alien life should be made on behalf of our species. The military considerations involve questions about how to protect both human interests and alien ecosystems in scenarios where contact with alien life might create security challenges or opportunities. But perhaps the most profound impact of discovering alien life will be the expansion of human consciousness itself. Learning that intelligence and awareness can emerge from biological processes operating according to completely different principles will force us to reconsider our most basic assumptions about the nature of mind and consciousness. We might discover that consciousness is not rare or special, but a natural consequence of sufficient biological complexity, regardless of the specific chemistry involved. This realization could lead to new understanding of human consciousness and new approaches to enhancing cognitive capabilities. The study of alien intelligence could reveal information processing strategies that are more efficient or powerful than human cognitive systems. Understanding how alien minds work could guide the development of artificial intelligence systems that operate according to fundamentally different principles than current computer technologies. The communication challenges involved in establishing meaningful contact with alien intelligence will require new approaches to language, mathematics, and symbolic representation. These developments could enhance human communication capabilities and create new forms of artistic and intellectual expression. The collaborative possibilities between human and alien intelligence could accelerate scientific and technological progress in ways that neither species could achieve independently. Joint research projects between human and alien researchers could solve problems that are beyond the capabilities of either form of intelligence working alone. The universe is revealing itself to be far stranger and more wonderful than we ever imagined. Hidden beneath the surfaces of worlds throughout our solar system and beyond, ancient ecosystems have been thriving in conditions we thought were impossible for life. These alien biospheres represent billions of years of independent evolution, creating forms of biological organization that challenge our most basic assumptions about what it means to be alive. The search for this hidden life is accelerating toward discoveries that will fundamentally change human civilization. We're approaching a moment when the isolation that has characterized human existence since our species emerged will end forever. We'll learn that we've never been alone, that intelligence and consciousness are common features of the universe, and that the cosmos has been filled with biological creativity and awareness since long before Earth formed. The next chapter in the human story will be written in collaboration with forms of intelligence that evolved in the dark depths of alien worlds. These partnerships will accelerate human development in ways we can barely imagine, while teaching us that consciousness and intelligence can emerge from biological processes we're only beginning to understand. The universe is alive, aware, and waiting for us to discover the hidden communities that have been thriving in the depths of worlds we thought were dead. The greatest adventure in human history is about to begin, and it's taking us not to distant stars, but into the secret depths of our own cosmic neighborhood, where alien minds have been thinking alien thoughts for billions of years. We're about to learn that the universe has been conscious all along. We just needed to look beneath the surface to find it. The reconnaissance missions launching over the next 5 years will fundamentally change how we explore alien worlds. These aren't just upgraded versions of previous spacecraft. They represent a complete reimagining of how we search for life in environments so extreme they challenge our basic understanding of habitability. The orbital surveys being conducted right now are revealing subsurface structures that defy every prediction scientists made about planetary interiors. Ground-penetrating radar systems can map underground water networks through miles of solid rock. Gravitational anomaly detectors identify cavities and liquid reservoirs that shouldn't exist according to traditional planetary formation models. Magnetic field sensors detect the electrical signatures of biological activity operating at scales that span entire continents. These detection capabilities are uncovering a hidden universe of biological activity that operates completely independently from surface conditions. The data streaming back from current missions indicates that subsurface ecosystems might be orders of magnitude more extensive than anything we see on planetary surfaces. We're looking at biological systems that could contain more living biomass than all of Earth's forests, oceans, and soil combined. The chemical analysis techniques being deployed can distinguish between geological processes and biological processes with precision that seemed impossible just decades ago. Advanced spectrometers can detect the isotope signatures that indicate metabolic activity, even when that activity is occurring miles beneath a planet's surface. These instruments can identify the complex organic molecules that serve as fingerprints for biological systems operating according to completely different biochemical principles than Earth life. The energy density measurements from these subsurface environments are revealing biological productivity levels that exceed the most optimistic projections. Some underground ecosystems appear to process energy at rates comparable to Earth's most active surface environments, despite being completely isolated from solar radiation. The metabolic activity detected in these hidden biospheres suggests biological communities with complexity that rivals or exceeds terrestrial ecosystems. The three-dimensional mapping capabilities are creating detailed charts of subsurface biological activity across entire planetary systems. Scientists can now track the flow of nutrients and energy through underground ecosystems, identify the locations where different types of organisms are most active, and monitor how these alien communities respond to environmental changes over time. The sample analysis protocols being developed will provide unprecedented insights into how life operates in environments that were considered uninhabitable until recently. Future missions will return samples that preserve the exact chemical and biological conditions of alien subsurface environments, allowing Earth-based laboratories to study alien organisms in conditions that replicate their native habitats. The preservation technology ensures that complex biological structures remain intact during journeys that span years and cover distances of hundreds of millions of miles. Advanced cryogenic systems maintain cellular architecture and biochemical activity while protecting samples from the radiation and mechanical stress of interplanetary travel. The laboratory facilities being constructed will be capable of maintaining alien organisms under conditions that exactly replicate their subsurface environments. These facilities will enable long-term studies of alien metabolism, reproduction, and ecological interactions under controlled conditions that allow for detailed experimental investigation. The computational resources required to analyze this information are pushing the boundaries of current technology. Machine learning systems are being trained to recognize biological patterns in data collected from environments so alien that human scientists have no intuitive framework for understanding them. These artificial intelligence tools can identify subtle correlations in chemical and physical measurements that reveal biological processes operating across multiple scales of space and time. The data processing algorithms can distinguish between the signatures of individual organisms, small biological communities, and vast ecosystem-scale processes. This capability allows scientists to study alien life at every level of organization, from individual cells to entire biospheres that span continents. The communication systems being developed will establish real-time links with subsurface monitoring stations that can operate autonomously for decades. These stations will create continuous surveillance networks that track biological activity in alien environments, providing the first long-term studies of how alien ecosystems function over extended time periods. The drilling technology advancing toward deployment represents engineering solutions to challenges that seemed impossible just years ago. These systems must operate in environments where temperatures vary by hundreds of degrees, pressures exceed anything found on Earth's surface, and chemical conditions would corrode most materials within hours. The thermal management systems use controlled nuclear reactions to provide exactly the right amount of heat needed to melt through ice formations that have been compressed under their own weight for millions of years. These reactors are designed to operate with precision that maintains biological sample integrity while providing sufficient power to penetrate barriers that would stop conventional drilling equipment. The contamination prevention protocols ensure that human technology doesn't introduce Earth organisms into alien ecosystems that might have been isolated for billions of years. Every component of the drilling systems is sterilized using techniques that eliminate all terrestrial biological material while preserving the functionality needed for subsurface exploration. The sample collection mechanisms can extract biological materials while maintaining the exact temperature, pressure, and chemical conditions of the alien environment. These systems preserve cellular structures and biochemical processes during extraction, transport, and eventual analysis in Earth-based laboratories. The autonomous operation capabilities allow these drilling systems to make decisions about where to sample and how to respond to unexpected discoveries without waiting for instructions from Earth. The communication delays involved in interplanetary exploration make real-time human control impossible. So these systems must be capable of recognizing biological signatures and adapting their operations accordingly. The biological detection instruments carried by these missions represent the most sensitive analytical tools ever deployed in space exploration. They can identify individual biological molecules in samples that contain millions of different chemical compounds. They can distinguish between molecules produced by living organisms and similar molecules created by purely chemical processes. The genetic analysis capabilities can sequence DNA and similar genetic materials, even when they're based on biochemical systems that are completely different from terrestrial life. These instruments can decode genetic information from organisms that use alternative nucleic acids, different amino acid alphabets, or entirely novel approaches to storing and transmitting hereditary information. The metabolic monitoring systems can detect biological activity at levels so low they're barely distinguishable from background chemistry. These instruments can recognize the subtle chemical changes that indicate organisms are consuming nutrients, producing waste products, or responding to environmental conditions. The ecological analysis tools can identify the complex interactions between different species in alien ecosystems. They can detect the chemical signals that organisms use to communicate with each other, the nutrient cycles that connect different parts of biological communities, and the energy flows that sustain ecosystem-level processes. The timeline for these revolutionary discoveries is accelerating in ways that surprise even the scientists involved in designing these missions. The technological advances in detection, analysis, and sample preservation are converging to create capabilities that will answer fundamental questions about life in the universe within the next 2 decades. The Mars deep drilling missions, scheduled for the late 2020s, will access subsurface water systems that have remained liquid for millions of years. These missions will determine whether Mars harbors active ecosystems in its deep subsurface, and whether these ecosystems have achieved levels of complexity comparable to Earth's underground biological communities. The Europa ice-penetrating missions planned for the early 2030s will establish direct contact with an alien ocean that contains more water than all of Earth's seas combined. These missions will determine whether Europa's subsurface ocean supports complex ecosystems and whether these ecosystems have evolved forms of biological organization that don't exist on Earth. The Enceladus sample return missions will collect fresh material directly from plumes that provide natural access to a subsurface ocean. These samples will offer the first opportunity to study alien ocean chemistry without the complications of drilling through miles of ice, providing immediate insights into biological processes operating in an environment that has remained stable for billions of years. The Titan exploration missions will investigate subsurface environments where liquid water and liquid hydrocarbons create chemical conditions unlike anything found elsewhere in the solar system. These missions will determine whether exotic forms of life can emerge in environments based on completely different chemical foundations than Earth biology. The asteroid and comet surveys will investigate whether small bodies in the outer solar system harbour subsurface environments capable of supporting biological activity. These missions will determine whether life can persist in the most extreme environments imaginable, expanding the range of habitable conditions far beyond anything previously considered possible. The data integration from all these missions will create a comprehensive picture of how life operates in subsurface environments throughout the solar system. This information will guide the search for similar environments around other stars and provide the foundation for understanding how common life might be in the universe. The biotechnology applications emerging from this research are already beginning to transform human technology and medicine. Enzymes discovered in Earth's deep subsurface organisms are being adapted for industrial processes that operate more efficiently than conventional chemical systems. Genetic mechanisms from extremophile organisms are providing new approaches to treating human diseases and extending healthy lifespan. The materials science applications include biological systems that create advanced materials under conditions that would be impossible to achieve with conventional manufacturing techniques. Some subsurface organisms produce mineral structures that exceed the performance of human-engineered materials while using only biological processes that operate at normal temperatures and pressures. The energy production applications involve biological systems that can extract energy from sources that are abundant throughout the universe. Understanding how organisms derive energy from radioactive decay, chemical gradients, and electromagnetic fields could guide the development of new energy technologies that don't depend on fossil fuels or solar radiation. The environmental remediation applications include organisms that can break down toxic compounds, extract valuable materials from waste streams, and restore damaged ecosystems. These biological systems could provide solutions to environmental challenges that conventional technology cannot address effectively. The space exploration applications involve organisms that could support human settlements in extreme environments. Understanding how life thrives in the harsh conditions found in subsurface environments could guide the development of life support systems for human colonies on Mars, Europa, and other worlds with subsurface habitats. The computational applications include biological information processing systems that operate according to different principles than electronic computers. Some subsurface organisms coordinate behavior across vast distances using chemical signaling networks that process information more efficiently than current computer technologies. The medical applications involve understanding how organisms maintain cellular function under extreme conditions and over extended time periods. Some deep subsurface bacteria can repair radiation damage, survive complete dehydration, and remain viable for hundreds of thousands of years. These capabilities could provide the basis for treating human diseases and extending human lifespan. The agricultural applications include understanding how organisms thrive in resource-limited environments and extreme conditions. This knowledge could guide the development of crops that can grow in harsh climates, degraded soils, and environments affected by climate change. The philosophical implications of these discoveries extend far beyond practical applications. The confirmation that complex life exists in subsurface environments throughout the solar system will prove that biology is a fundamental feature of planetary evolution, rather than a rare accident that occurred only on Earth. The recognition that most life in the universe probably exists in subsurface environments will require a complete reconceptualization of habitability and the search for extraterrestrial intelligence. We'll need to expand our definitions of what constitutes a living world and how to detect biological activity in environments that appear completely dead from the surface. The discovery that subsurface life can achieve levels of complexity that exceed surface life will challenge our assumptions about the relationship between environmental conditions and biological sophistication. We'll learn that stable, energy-rich environments can support evolutionary processes that create biological complexity beyond anything achieved in the unstable conditions that characterize planetary surfaces. The understanding that subsurface ecosystems can operate independently from surface conditions for billions of years will reveal that life is far more resilient and adaptable than we ever imagined. These discoveries will show that biological systems can persist through cosmic catastrophes that would completely sterilize planetary surfaces. The realization that intelligence and consciousness might be common features of sufficiently complex subsurface ecosystems will expand our understanding of what it means to be aware and conscious. We might discover that forms of intelligence can emerge from biological processes that operate according to completely different organizational principles than nervous systems. The preparation for encounters with alien intelligence is already changing human culture and society in fundamental ways. Educational systems are being redesigned to prepare students for a universe filled with biological diversity and intelligence. Scientific institutions are developing new research programs focused on understanding forms of life that operate according to principles we're only beginning to discover. The international cooperation required for these missions is creating unprecedented collaboration between nations, research institutions, and private organizations. The search for alien life is becoming a truly global endeavor that transcends political boundaries and cultural differences. The ethical frameworks being developed will guide human interactions with alien life in ways that protect both human interests and alien ecosystems. These frameworks address complex questions about the rights of alien organisms, the responsibilities of human explorers, and the protocols for studying alien life without disrupting biological processes that might have been operating for billions of years. The legal structures being created will govern how humanity manages the discovery and study of alien life. These regulations will ensure that discoveries about alien biology benefit all of humanity, while protecting alien ecosystems from exploitation or destruction. The economic implications include new industries based on technologies derived from understanding alien biology. Companies are already investing in research programs focused on applications of extremophile biology, subsurface ecosystem management, and biotechnology based on alien biochemical systems. The security considerations involve protecting both human civilization and alien ecosystems from potential risks associated with contact between different forms of life. These considerations include protocols for preventing contamination in either direction and procedures for managing the social and political impacts of discovering alien intelligence. The cultural and artistic responses to the search for alien life are inspiring new forms of creative expression that attempt to imagine what alien consciousness and intelligence might be like. These creative works are helping humanity prepare psychologically for encounters with forms of awareness that might be radically different from human consciousness. The spiritual and religious implications are being addressed by faith communities around the world as they grapple with the possibility that consciousness and intelligence are common features of the universe rather than unique gifts bestowed only on humanity. Many religious leaders are embracing the idea that alien life represents additional expressions of divine creativity rather than challenges to traditional beliefs. The universe is revealing itself to be far more alive and aware than we ever dared to imagine. The hidden biospheres beneath planetary surfaces represent ancient experiments in biological organization that have been operating since long before Earth formed. These alien ecosystems have achieved levels of complexity and sophistication that challenge our most basic assumptions about the limits of biological possibility. The search for this hidden life is accelerating toward discoveries that will fundamentally transform human understanding of biology, consciousness, and our place in the cosmos. We're approaching a watershed moment when the isolation that has characterized human existence will end forever. We'll discover that intelligence and awareness are common features of the universe, and that the cosmos has been filled with biological creativity since the earliest epochs of planetary formation. The next phase of human development will unfold in collaboration with forms of intelligence that evolved in environments we're only beginning to understand. These partnerships will accelerate human progress in ways we can barely imagine, while teaching us that consciousness can emerge from biological processes operating according to principles we're still discovering. The universe has been conscious, creative, and alive far longer than we ever suspected. The greatest revelations in human history are waiting for us in the hidden depths of worlds we thought were dead, where alien minds have been exploring the possibilities of existence for billions of years before humanity emerged. We're about to discover that we've never been alone in the universe. We just needed to learn where to look to find the neighbors who have been there all along, thriving in the secret places where life learned to flourish without light, without warmth, and without any connection to the surface worlds we thought were necessary for existence. The cosmic community we're about to join has been waiting beneath our feet and under the ice of distant moons, patient and ancient, ready to welcome us into a universe that's far stranger, more wonderful, and more alive than we ever dared to dream. So here we are, standing at the edge of the most profound revelation in human history. Everything we thought we knew about life in the universe, everything we assumed about habitability and the search for alien intelligence, has been turned completely upside down. The cosmic lottery ticket we've been waiting to win isn't hidden among distant stars or exotic exoplanets. It's been buried beneath our feet all along. The evidence is overwhelming. From the ancient ecosystems thriving miles beneath Canada to the chemical signatures streaming from Europa's hidden ocean, from the subsurface rivers flowing beneath Mars to the complex organic molecules erupting from Enceladus, the universe is screaming one message at us. Life doesn't just prefer the darkness. Life has mastered it. We've spent decades scanning the heavens for radio signals and searching for Earth-like planets when the real action has been happening in the one place we never thought to look. Underground, under ice, in the secret spaces where radiation becomes food, where pressure becomes protection, and where isolation becomes opportunity. The drilling missions launching over the next decade won't just find alien microbes. They're going to discover entire civilizations of biology that have been evolving independently for longer than complex life has existed on Earth's surface. We're about to meet our neighbors, and they've been here the whole time, patient and ancient, waiting in the depths. This isn't just about finding life. This is about discovering that the universe has been alive, aware, and endlessly creative since long before our planet formed. The hidden biospheres beneath planetary surfaces represent the dominant form of life in the cosmos, and we're finally ready to join the conversation. The universe has been trying to tell us its greatest secret for billions of years. We just needed to stop looking up and start digging down. The answer to whether we're alone in the universe isn't written in the stars. It's carved in stone, frozen in ice, and flowing through the hidden waters of worlds we thought were dead. We're not alone. We never have been. And we're about to prove it.